The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today we are going to continue looking at critical points, and we'll learn how to actually decide whether a critical point is a minimum, a maximum, or a saddle point. So that's the main topic for today. So remember, yesterday we looked at critical points of functions of several variables. And so a critical point of a function, say, of two variables x and y, that's a point where the partial derivatives are both 0. And we've seen that there's various kinds of critical points. There's local minima. So maybe I should show the function and its contour plot. There's local maxima, which are like that, and there's saddle points, which are neither minima nor maxima. And of course, if you have a real function, then it will be more complicated. It will have several critical points. So this example here, well, you see on the plot that there's two maxima, and there's in the middle between them, there's a saddle point. And actually you can see them on the contour plot. On the contour plot, you see the maxima because the level curves become circles that narrow down and shrink to the maximum. And you can see the saddle point because here you have this level curve that makes a figure 8. It crosses itself. And if you move up or down here, then, so along the y direction, the values of the function will decrease. Along the x direction, the values will increase. So you can see, usually, quite easily, where are the critical points just by looking either at the graph or at the contour plot. So the only thing with the contour plot is you need to read the values to tell a minimum from a maximum, because the contour plots look the same, just, of course, in one case the values increase, in the other one they decrease. So the question is, how do we decide between the various possibilities? So local minimum, local maximum, or saddle point. So, and in fact, why do we care? Well, the other question is, how do we find the global minimum or maximum of a function? So here already I should point out, well, first of all, to decide where the function is the largest, in general, you'll have actually to compare the values. For example, here, if you want to know what is the maximum of this function, well, we have two obvious candidates. We have this local maximum and that local maximum. And the question is, which one is the higher of the two? Well, in this case, actually, they're exactly tied for maximum. But in general, you would have to compute the function at both points and compare the values. If you know that it's 3 at one of them and 4 at the other, well, 4 wins. The other thing that you see here is if you're looking for the minimum of this function, well, the minimum is not going to be at any of the critical points. So where's the minimum? Well, it looks like the minimum is actually out there on the boundary or at infinity. So that's another feature. The global minimum or maximum doesn't have to be at a critical point. It could also be somehow on the side, in some limiting situation where one variable stops being in the allowed range of values or goes to infinity. So we have to actually check the boundary and the infinity behavior of our function to know where actually the minimum and maximum will be. So in general, I should point out, these could occur either at a critical point or on the boundary or at infinity. So by that I mean on the boundary of a domain of definition that we are considering. And so we have to try both. Okay, so we'll get back to that. For now, let's try to focus on the question of what's the type of the critical point. So we'll use something that's known as the second derivative test. And in principle, well, the idea is kind of similar to what you do with a function of one variable, namely a function of one variable. If the derivative is 0, then you know that you should look at the second derivative, and that will tell you whether it's curving up or down, whether you have a local max and a local min. And the main problem here is, of course, we have more possible situations and we have several derivatives. So actually we have to think a bit harder about how we'll decide. But it will again involve the second derivatives. Okay, so let's start with just an easy example that will be useful to us because actually it will provide the basis for the general method. Okay, so we are first going to consider a case where we have a function that's actually just quadratic. So let's say I have a function w of xy that's of the form ax squared plus bxy plus cy squared. Okay, so this guy has a critical point at the origin, right? Because if you take the derivative with respect to x, well, and if you plug x equals y equals 0, you'll get 0. And same with respect to y. You can also see if you try to do a linear approximation of this, well, all these guys are much smaller than x and y when x and y are small. So the linear approximation, the tangent plane to the graph, is really just w equals 0. Okay, so how do we do it? Well, yesterday we actually did an example. It was a bit more complicated than that, but let me do it. So remember, we were looking at something that started with x squared plus 2xy plus 3y squared. And there were other terms, but let's forget them now. And what we did is we said, well, we can rewrite this as x plus y squared plus 2y squared. And now this is a sum of two squares. So each of these guys has to be non-negative, and so the origin will be a minimum.